The 2004 Indian Ocean earthquake occurred at 0 hours 58 minutes and 53 seconds UTC on the 26th of December, with the epicenter off the west coast of Sumatra, Indonesia. The shock had a moment magnitude of 9.1 to 9.3 and a maximum Mercalli intensity of IX. The Undersea Megathrust earthquake was caused when the Indian plate was subducted by the Burma Plate and triggered a series of devastating tsunamis along the coasts of most land masses bordering the Indian Ocean, killing 230,000 people in 14 countries, and inundating coastal communities with waves up to 30 meters high. It was one of the deadliest natural disasters in recorded history. Indonesia was the hardest hit country, followed by Sri Lanka, India, and Thailand. It is the third largest earthquake ever recorded on a seismograph and had the longest duration of faulting ever observed, between 8.3 and 10 minutes. It caused the entire planet to vibrate as much as 1 centimeter and triggered other earthquakes as far away as Alaska. Its epicenter was between Simeulue and mainland Indonesia. The plight of the affected people and countries prompted a worldwide humanitarian response. In all, the worldwide community donated more than $14 billion in humanitarian aid. The event is known by the scientific community as the Sumatra earthquake. The resulting tsunami was given various names, including the 2004 Indian Ocean tsunami, South Asian tsunami, Indonesian tsunami, the Christmas tsunami, and the Boxing Day tsunami. Earthquake characteristics. The earthquake was initially documented as moment magnitude 8.8. In February 2005, scientists revised the estimate of the magnitude to 9.0. Although the Pacific Tsunami Warning Center has accepted these new numbers, the United States Geological Survey has so far not changed its estimate of 9.1. The most recent studies in 2006 have obtained a magnitude of MW 9.1 to 9.3. Dr. Haru Kanamori of the California Institute of Technology believes that MW 9.2 is a good representative value for the size of this great earthquake. The hypocenter of the main earthquake was approximately 160 kilometers off the western coast of northern Sumatra, in the Indian Ocean just north of Simeulue Island at a depth of 30 kilometers below mean sea level. The northern section of the Sunda Megathrust ruptured over a length of 1,300 kilometers. The earthquake was felt simultaneously in Bangladesh, India, Malaysia, Myanmar, Thailand, Singapore, and the Maldives. Splay faults, or secondary pop-up faults, caused long, narrow parts of the seafloor to pop up in seconds. This quickly elevated the height and increased the speed of waves, causing the complete destruction of the nearby Indonesian town of Longa. Indonesia lies between the Pacific Ring of Fire along the northeastern islands adjacent to New Guinea, and the Alpide belt that runs along the south and west from Sumatra, Java, Bali, Flores to Timor. Great earthquakes such as the Sumatra event, which are invariably associated with megathrust events in subduction zones, have seismic moments that can account for a significant fraction of the global earthquake moment across century-scale time periods. Of all the seismic moment released by earthquakes in the 100 years from 1906 through 2005, roughly 1/8 was due to the Sumatra event. This quake, together with the Good Friday earthquake and the Great Chilean earthquake, account for almost half of the total moment. The much smaller but still catastrophic 1906 San Francisco earthquake is included in the diagram for perspective. MW denotes the magnitude of an earthquake on the moment magnitude scale. Since 1900, the only earthquakes recorded with a greater magnitude were the 1960 Great Chilean Earthquake and the 1964 Good Friday Earthquake in Prince William Sound. The only other recorded earthquakes of magnitude 9.0 or greater were off Kamchatka, Russia, on the 4th of November 1952 and Tohoku, Japan in March 2011. Each of these megathrust earthquakes also spawned tsunamis in the Pacific Ocean. However, the death toll from these was significantly lower, primarily because of the lower population density along the coasts near affected areas and the much greater distances to more populated coasts, and also due to the superior infrastructure and warning systems in MEDCs such as Japan. Other very large megathrust earthquakes occurred in 1868, 1827, 1812, and 1700. All of them are believed to be greater than magnitude 9, but no accurate measurements were available at the time. Foreshock. The 2002 Sumatra earthquake is believed to have been a foreshock, predating the main event by over 2 years. Tectonic Plates. The megathrust earthquake was unusually large in geographical and geological extent. An estimated 1,600 kilometers of fault surface slipped about 15 meters along the subduction zone where the Indian Plate slides under the overriding Burma Plate. The slip did not happen instantaneously but took place in 2 phases over a period of several minutes. Seismographic and acoustic data indicate that the first phase involved a rupture about 400 kilometers long and 100 kilometers wide, located 30 kilometers beneath the seabed, the largest rupture ever known to have been caused by an earthquake. The rupture proceeded at a speed of about 2.8 kilometers per second, beginning off the coast of ACEH and proceeding northwesterly over a period of about 100 seconds. A pause of about another 100 seconds took place before the rupture continued northwards towards the Andaman and Nicobar Islands. However, the northern rupture occurred more slowly than in the south, at about 2.1 kilometers per second, continuing north for another 5 minutes to a plate boundary where the fault type changes from subduction to strike-slip. The Indian Plate is part of the Great Indo-Australian Plate, which underlies the Indian Ocean and Bay of Bengal, and is drifting northeast at an average of 6 centimeters per year. The India Plate meets the Burma Plate at the Sunda Trench. At this point, the India Plate subducts beneath the Burma Plate, which carries the Nicobar Islands, the Andaman Islands, and northern Sumatra. The India Plate sinks deeper and deeper beneath the Burma Plate until the increasing temperature and pressure drive volatiles out of the subducting plate. These volatiles rise into the overlying plate, causing partial melting and the formation of magma. The rising magma intrudes into the crust above and exits the Earth's crust through volcanoes in the form of a volcanic arc. The volcanic activity that results as the Indo-Australian Plate subducts the Eurasian Plate has created the Sunda Arc, as well as the sideways movement between the plates. The sea floor is estimated to have risen by several meters, displacing an estimated 30 cubic kilometers of water and triggering devastating tsunami waves. The waves did not originate from a point source, as was inaccurately depicted in some illustrations of the paths of travel, but rather radiated outwards along the entire 1,600-kilometer length of the rupture. This greatly increased the geographical area over which the waves were observed, reaching as far as Mexico, Chile, and the Arctic. The raising of the sea floor significantly reduced the capacity of the Indian Ocean, producing a permanent rise in the global sea level by an estimated 0.1 millimeters. Aftershocks and other earthquakes. Numerous aftershocks were reported off the Andaman Islands, the Nicobar Islands and the region of the original epicenter in the hours and days that followed. The magnitude 8.7 2005 near-similar earthquake, which originated off the coast of the Sumatran island of Nias, is not considered an aftershock, despite its proximity to the epicenter, and was most likely triggered by stress changes associated with the 2004 event. This earthquake was so large that it produced its own aftershocks and presently ranks as the 7th largest earthquake on record since 1900. Other aftershocks of up to magnitude 6.6 continued to shake the region daily for up to 3 or 4 months. As well as continuing aftershocks, the energy released by the original earthquake continued to make its presence felt well after the event. A week after the earthquake, its reverberations could still be measured, providing valuable scientific data about the Earth's interior. The 2004 Indian Ocean earthquake came just 3 days after a magnitude 8.1 earthquake in an uninhabited region west of New Zealand's subantarctic Auckland Islands, and north of Australia's Macquarie Island. This is unusual, since earthquakes of magnitude 8 or more occur only about once per year on average. However, the U.S. Geological Survey sees no evidence of a causal relationship between these events. The December earthquake is thought to have triggered activity in both Lusa Mountain and Mount Talang, volcanoes in Aceh province along the same range of peaks, while the 2005 near-similar earthquake had sparked activity in Lake Toba, an ancient crater in Sumatra. The energy released on the Earth's surface only by the 2004 Indian Ocean earthquake and tsunami was estimated at 1.1 times 1017 joules, or 26 megatons of TNT. This energy is equivalent to over 1,500 times that of the Hiroshima atomic bomb, but less than that of Tsar Bomba, the largest nuclear weapon ever detonated. However, the total work done MW by this quake was 4.0 times 1022 joules, the vast majority underground. This is over 360,000 times more than its ME, equivalent to 9,600 gigatons of TNT equivalent, or about 370 years of energy use in the United States at 2005 levels of 1.08 times 1020 J. The only recorded earthquakes with a larger MW were the 1960 Chilean and 1964 Alaskan quakes, with 2.5 times 1023 joules and 7.5 times 1022 joules respectively. The earthquake generated a seismic oscillation of the Earth's surface of up to 20 to 30 centimeters, equivalent to the effect of the tidal forces caused by the Sun and Moon. The shock waves of the earthquake were felt across the planet, as far away as the U.S. state of Oklahoma, where vertical movements of 3 mm were recorded. By February 2005, the earthquake's effects were still detectable as a 20 micrometers complex harmonic oscillation of the Earth's surface, which gradually diminished and merged with the incessant free oscillation of the Earth more than 4 months after the earthquake. Because of its enormous energy release and shallow rupture depth, the earthquake generated remarkable seismic ground motions around the globe, particularly due to huge Rayleigh elastic waves that exceeded 1 centimeter in vertical amplitude everywhere on Earth. The record section plot displays vertical displacements of the Earth's surface recorded by seismometers from the IRIS-USGS Global Seismographic Network, plotted with respect to time on the horizontal axis, and vertical displacements of the Earth on the vertical axis. The seismograms are arranged vertically by distance from the epicenter in degrees. The earliest, lower amplitude, signal is that of the compressional wave, which takes about 22 minutes to reach the other side of the planet. The largest amplitude signals are seismic surface waves that reach the antipode after about 100 minutes. The surface waves can be clearly seen to reinforce near the antipode, and to subsequently encircle the planet to return to the epicentral region after about 200 minutes. A major aftershock can be seen at the closest stations starting just after the 200-minute mark. This aftershock would be considered a major earthquake under ordinary circumstances, but is dwarfed by the main shock. The shift of mass and the massive release of energy very slightly altered the Earth's rotation. The exact amount is not yet known, but theoretical models suggest the earthquake shortened the length of a day by 2.68 microseconds. Due to a decrease in the oblateness of the Earth, it also caused the Earth to minutely wobble on its axis by up to 2.5 centimeters in the direction of 145 degrees east longitude, or perhaps by up to 5 or 6 centimeters. However, because of tidal effects of the Moon, the length of a day increases at an average of 15 microseconds per year, so any rotational change due to the earthquake will be lost quickly. Similarly, the natural Chandler wobble of the Earth, which in some cases can be up to 15 meters, will eventually offset the minor wobble produced by the earthquake. More spectacularly, there was 10 meters movement laterally and 4 to 5 meters vertically along the fault line. Early speculation was that some of the smaller islands southwest of Sumatra, which is on the Burma Plate, might have moved southwest by up to 36 meters. But more accurate data released more than a month after the earthquake found the movement to be about 20 centimeters. Since movement was vertical as well as lateral, some coastal areas may have been moved to below sea level. The Andaman and Nicobar Islands appear to have shifted southwest by around 1.25 meters and to have sunk by 1 meter. In February 2005, the Royal Navy vessel HMS Scott surveyed the seabed around the earthquake zone, which varies in depth between 1,000 and 5,000 meters. The survey, conducted using a high-resolution, multi-beam sonar system, revealed that the earthquake had made a huge impact on the topography of the seabed. 1,500-meter high thrust ridges created by previous geologic activity along the fault had collapsed, generating landslides several kilometers wide. One such landslide consisted of a single block of rock some 100 meters high and 2 kilometers long. The momentum of the water displaced by tectonic uplift had also dragged massive slabs of rock, each weighing millions of tons, as far as 10 kilometers across the seabed. An oceanic trench several kilometers wide was exposed in the earthquake zone. The TOPEX, Poseidon and Jason-1 satellites happened to pass over the tsunami as it was crossing the ocean. These satellites carry radars that measure precisely the height of the water surface. Anomalies of the order of 50 centimeters were measured. Measurements from these satellites may prove invaluable for the understanding of the earthquake and tsunami. Unlike data from tide gauges installed on shores, measurements obtained in the middle of the ocean can be used for computing the parameters of the source earthquake without having to compensate for the complex ways in which close proximity to the coast changes the size and shape of a wave.